This video for Physics 12 actually contains the last two lessons for the chapter, lessons that are in boxes 8 and in boxes 9. Before we get into some notes that you'll probably want to write down, I just want to go over some notes that you already have, so you don't need to copy these at all. You've already got these. Earlier on in the chapter, at the very beginning, we talked about how work is just a dot product of force and distance, so they're kind of supposed to be going the same direction. That's what the dot product is all about. And a big thing for the first half of the chapter was conservation of energy. Really useful organizational tool to help you solve a lot of problems, especially ones that involve forces and distances. One key thing that we had to be careful about was the force of gravity. It diminishes as you go higher up into the sky, and so we had to use a more exotic version of potential energy, but we were able to use that within the conservation of energy equation. We also looked at power. Power is just either work or energy divided by time. It's joules per second, otherwise known as watts. And this now is kind of the last part of the chapter. We started on it a couple of classes ago. We were looking at momentum and impulse and how impulse actually causes changes in momentum. And down there at the bottom of the page was our plan for collisions, how momentum is conserved. If you add up all the initial momentum, you have to get the exact same number finally. And we've been doing some one-dimensional collisions, and we've been looking at them as either being elastic or inelastic. And we said if it's elastic, then none of the kinetic energy is converted to heat or sound. It's all conserved, it's constant. And inelastic ones, we do have some heat or sound that's created. So far, we've only been doing one-dimensional collisions, and here's where we finish it off. Still in section G of your notes, we're going to do part 2, two-dimensional collisions. And here you actually have two things to help you out. Momentum's going to help you twice. It's your best friend, and now it comes as a pair. You've got momentum in the x direction and momentum in the y direction being constant. So we're going to try a few examples out so you can see exactly how that works. And all three examples off the start are going to be inelastic collisions where some of that kinetic energy is going to get converted into heat. And we'll just take a look and see how those work. Then we'll do one elastic one at the end. So here's our first collision, a couple of objects here. Object A and B, they have different masses and they've got some speeds there, 4 and 2 meters per second. And it's clearly a two-dimensional collision. You can see that they're traveling in different directions. One's going east, one's going north, totally different dimensions here. So we have to treat this very differently than we did in Physics 11. Now, generally there are two styles of solutions, a vector solution and a component solution, and I'd like to show you both. But I did need to let you know one more little bit of information about this story. I have to tell you that they're going to stick together, and their goal here is to try to find that final velocity, how big, and in which direction are they going to be going afterwards. So this time we're going to do the vector method. It's probably going to be your favorite one. It's very pictorial, it's very fast, it's just a really nice method, and whenever we can, we're going to do this one. So we're actually just going to draw a picture that says, hey, look at this. All the initial momentums are equal to all the final momentums. But it is going to be about momentums. So you have to be looking at the product of mass and velocity. So 2 times 4 is 8, and then 3 times 2 is 6 for ball B. And so our picture off the start, I love using different colors here, so I might use green maybe for my initial momentums. So I've got an initial momentum of 8 to the east, and then another initial momentum that's 6 to the north, and I'm going to add those up as vectors, head to tail, so I have to connect those two arrows together that way. And the answer is not going to be 14, right? We'll have to use a little Pythagoras to figure out what that total actually is. Afterwards, I love switching colors, just to allow me to see what's going on visually here. Afterwards, they stick together, there's one big momentum, and it's going to have to be the exact same size as that combination of the 8 and the 6. This one's actually pretty nice. It's just going to be some Pythagoras, right angle triangle, little SOHCAHTOA. Trigonometry will be done. Be careful though, make sure that when you're drawing these pictures that you're using momentum. So the momentum values are 8 and 6. We can't use just the speeds of 4 and 2. Okay, well, I can find the size of that momentum just by doing Pythagoras. Looks like that momentum value is 10, and then I can divide by that total mass. The total mass now is 5 kilograms, and I can divide by the 5 and see that the speed needs to be 2 meters per second. The angle's pretty quick too. I can just use tangent backwards, little inverse tan. Looks like that angle is 37 degrees. Okay, so this question's pretty much done. Looks like our final velocity here is 2 meters per second, and that's the speed anyways, and then the angle is 37 degrees north of east. So feel free to pause these videos at any time to write the notes down. I'm just going to keep on going, that way I can keep the video file a little bit shorter. Now that question's essentially done. You have found that final velocity and the angle to it, so that you found a couple of things. I'm just going to scroll that up a little bit. Here's what you already know. You don't really need to rewrite that. You've already kind of figured this all out. They started off as separate items, and now they're combined as a 5 kilogram blob. And now we're going to go and check and see if it's elastic. And we kind of know it's going to be inelastic. It's in the inelastic section in your notes. But this is what I would expect you to be able to do. At the end of doing conservation momentum, you can do a little check for elasticity. So I'm going to go and check out the kinetic energy total before they touch each other. So I'm just doing 1/2 mv squared. Don't have to worry about direction at all. Energy just doesn't care. And that total is 22 joules of moving energy. Now, afterwards, when they become a 5 kilogram blob, what's going on there? I don't know. We'll go find out. So 1/2 the mass of 5 times the speed of 2 squared, and, oh, disappointing, it's only 10 joules. So we could look at that as physicists and go, you had 22 joules before, now you're down to 10, you lost 12 to heat and sound. This thing is not elastic. No surprise, it's in the inelastic section of your notes, but that's generally our plan. Wait till the end and then go and check and see whether or not it's elastic or not. Okay, we're going to do just 2 more examples, actually, of this 2-dimensional collision stuff. The next one is going to be a little different. You won't be able to use that picture method to find the story in the end. We're going to start off with the same picture, okay, the same 2 objects, 2 and 3 kilograms, heading in those different dimension directions there, and they're going to collide, but this time they're not going to stick together. So the little bit of information I want to tell you is that ball A was seen leaving at 2.5 meters per second for a speed and an angle of 30 degrees up, 30 degrees north of east. So I've given you 2 bits of information afterwards, and very importantly here, I've hidden 2 things from you. This time I've hidden the speed and the angle for ball B. I'm able to hide 2 things from you because you have 2 helpers, momentum in the x and momentum in the y, creating math facts for you. So I can hide any 2 things. It could have been both angles, could have been both speeds. Here I'm hiding 1 speed and 1 angle. And we're going to try to find out what's going on with ball B. Here's the big problem with this one. You've got 2 momentums before they touch and 2 separate momentums later. That's 4 momentums. And if you were to draw this as a picture, you would end up with a quadrilateral. And we don't have very good quadrilateral skills. So if you notice that there are more than 3 momentums in the story, then you have to use this method called components. We're going to take that 2.5 meters per second, that speed, and we're going to resolve it. We're going to break it up into its components. Pretty easy to do. We can just use SOHCAHTOA to do it. We can go with cosine to find the x. Looks like that ball A is going sideways at 2.165. And it's also going up at 1.25 meters per second. Now, here comes the component game. Going to be honest, most students don't enjoy doing this unless they have to. They like the picture method instead. And with this method, you do 2 separate calculations, very much like Physics 11, but you have to do them twice, once in the x and once in the y. So we'll try this out here. In the x direction, here's my story about the momentum being constant. In the x direction, in the sideways direction, I have 8 units of momentum for ball A, and then this 0. You might be wondering, why 0? Well, ball B is not moving sideways at all at the beginning of the story, so it has no momentum sideways, even though it does have a momentum up and down. Afterwards, ball A has this much momentum sideways, and then here's ball B finishing it off. Now, let's look in the y direction. In the y direction, there's this big 0 for ball A at the beginning because ball A has no y, no up and down velocity to it, so it has no up and down momentum there. Ball B certainly does have up and down momentum. Here's ball A afterwards with a little bit of up and down momentum. Again, I'm using that component of the velocity there. And then here's ball B doing the rest. Now, pretty easy equations just to march through. You can go and find out those velocity values in the x and the y direction for ball B. It's got to be going sideways at 1.2 and up at 1.1, and now it's just kind of good style to push those back together into one nice little triangle, just a little bit of Pythagoras and trigonometry, and this thing is done pretty quick. So the Pythagoras gives us 1.69 meters per second, 44-degree angle north of east if we do a little trigonometry. Okay, so you found 2 things, right? You've got those 2 helpers, momentum in the x, momentum in the y, and you were able to find 2 numbers in the end. So your teacher can always hide 2 things from you, and you can find those 2 things. It's just not as fun using this component method. It's usually a little nicer using the vector method if you can. When you're finished, it is our expectation that you could say, all right, let's check for elasticity. You don't need to write this all down. I think we have this essentially already. We know they were both moving before and they're both moving later, and we're going to try to figure out whether or not this collision was elastic. We already know the total before they touched is the same as the last example, 22 joules. And now we can go and see how much moving energy we've got with both of them moving around later. They're both moving, but that doesn't tell me whether it's elastic or not. I have to check the kinetic energy. Kind of disappointing. Only 10.5 joules. So we've lost 11.5 joules there to heat and sound. This is not elastic. If those two numbers ever come out the same, then you can go, whoa, that one was elastic. Okay, we're going to do one more of these inelastic ones. It won't be a component question. It's going to be a vector one, but this time it won't have a nice right angle in it. So it's just a little bit more interesting. So here's the picture. The picture on the left probably needs a little explaining. The before picture has ball A rushing in towards ball B, and unlike the way I've drawn it there, it's actually going to hit it a little bit to the side. Sometimes people say obliquely. So it's going to hit it just to the side, and then afterwards they're going to scatter away at two different angles. It looks like A is going up and B is going down. At the beginning of this story, ball B is just going to be at rest. It's not going to be moving. Kind of like a pool game, a billiard game, where one ball's just sitting there and then the cue ball comes in. Now, as a teacher, as a person creating the question, I have to make sure there are only two things missing. And I think we're okay. I've given you one angle and another angle. So the only thing missing are the two speeds. So as long as I only hide two things from you, could have been both of the angles. Here it's both of the speeds or one of each, then that's fair. All right, I'm going to go with the picture method, with the vector method. I know that afterwards A goes up and to the right and B goes down and to the right. Okay, so I'm just going to say the initial momentum total has to equal the final momentum total. And initially, as far as totaling goes, well, it's all ball A. Ball B has no momentum. It's just sitting there at rest. So 8 times 4, just multiplying those together, gets me 32 kilogram meters per second. I have to get to the end of that vector with my final two momentums. So putting those two momentums together, A goes up and to the right, and then keep going, connect onto the end, B goes down and to the right. And that's going to make a sum that's equal to the blue one. Now I do know that ball A scatters up at 20 degrees, so I can put a 20 in here, and B goes down at 30. I might need to add a little reference line in there if it helps, right? So feel free to do that. Then you can do the alternate interior Z-shaped angle deal. And at that point, you could do like 180 degrees in a triangle, find out that that's 130. And now it's not a right angle triangle, but we are good to go. We have enough information. Actually, we have angle, side angle. We could do the sine law here, and it would work fine. But when you do the sine law here, you're going to find these momentum values, not the velocities, not the speeds, but that's easy to get back to speeds just by dividing by mass. So I've got a beautiful working pair, the 130 and the 32. I'm going to use them in my sine law. Now it's not even a physics question anymore, it's just a math question. So I do the sine law, and I find out that the final momentum of ball A is 20.8. Now that's a momentum value, it's kilogram meters per second. So I have to divide by the mass of 8 to see that its speed is 2.61. That works so well, I'm going to do exactly the same thing to find out what's going on with ball B. I find out that its momentum is 14, dividing by the mass of 10, it's got to be going 1.43. So that's an expectation that I'd have on you, that you'd be able to go and conserve momentum either with a picture like we've done here or with components if you have to, and then find two missing things. Then when you're done, I can ask you, hey, what do you think? Was it elastic? And you just check out the kinetic energies. So before they touch, only that 8 kilogram item is moving, the 10 still. Looks like we've got 64 joules of going fast energy. Okay, I check out the energy afterwards. Just going with 1/2 mv squared, direction doesn't matter. And I'm kind of hoping for 64. Oh, 37. Okay, so no, this one's not elastic. If they're both the same number, then it would have been an elastic collision. And so that's actually the first lesson. I guess it would be 3.8. And then on the next day on 3.9, we're going to look at, well, what happens if you know that it's elastic? What's that actually going to look like? And we're only going to do one special case because they can be incredibly challenging if you're not careful. So here goes. Part B of section 2 of part G. What if it's an elastic story where no energy, no kinetic energy is lost to heat or sound? So I need to give you a little picture. Imagine this is kind of like a pool game, but with some very heavy objects here. They're both 4 kilograms. Turns out that's important. We are only going to be able to do this if the masses are the same. Ball A is coming in at 12 meters per second, and ball B is just waiting to have a collision happen, and then they scatter away. And I'm only going to give you one little bit of information. Here it's one angle. So you are missing 3 things. You're missing the other angle for ball B and both speeds, but that's okay. I know you can find 2 things because of momentum, and I know you can find one more thing because you're told that it's elastic, that there's no loss of kinetic energy. Now, at this point, I would not write any more of these notes down. Just let your notes sit there for a minute, and I just want to show you something. It's best if you don't write the next stuff down. Okay, so here's what you could do. You could say, well, I could do conservation of momentum. There are only 3 momentums because ball B is at rest at the beginning. And I could draw a little picture. And I'm just going with lots of variables here. I'm not putting in any of the numbers. Now, mass A and mass B, they may often in stories be different, but not today. Here they're both the same. So I'm going to take that picture, that momentum triangle picture, and I'm going to divide everything by 4 kilograms. I'm going to divide everything by that mass that's the same for object A and B, and just have a little triangle that looks like that. And that just sits there, not much more I can do with it. So now I'm going to go and take a look at conservation of kinetic energy. Pretty intense looking, but a lot of it's going to go away. Like for starters, who needs all these halves? Forget them. They're just getting in the way. Next thing, normally you can't go and cancel the m's because they're different m's, but these m's are the same. And it's the only kind of elastic 2-dimensional collision we're going to do. So I'm going to cancel those m's. And there's even one more thing you can throw away. Ball B initially is not moving, so VBI is 0, so that's going away too. We have thrown away so much stuff it's hard to see what's left. So let me extract it and pull it down just so you can see it. And now when you stare at that equation and then you look at the picture up above, you can go, whoa, whoa, hang on. That's Pythagoras. That only happens for a right angle triangle. And it looks like this blue one is the hypotenuse, and the 2 green ones, which are those objects leaving the scene after the collision, they have to be actually at a 90-degree angle. So this is a neat little thing that has to be true. We're going to get a right angle triangle in there whenever it's this exact scenario. Okay, so let's go back to where you've got your notes. Here's what you can take to the bank. This is the only elastic 2-dimensional collision that I would ever give you. It's pretty specific. It says if it's elastic, you're told it's elastic, and it's 2-dimensional. You can see that happening. And they're equally massive. And one object is at rest. That's a lot of ifs, right? 4 ifs. But if all of those things are true, then this always happens. Those objects always leave each other at 90 degrees. Let me actually show you a little video here. I don't know if this video is going to show up super well, but we'll give it a try here. So here's a pool table. Going to try to take a shot on the 9 ball here. The white ball is going to hit the 9 ball at just the right angle, so the 9 ball is going to go into the corner pocket. But this is a losing shot because, as you can see with the carpenter's square that I've laid down, the cue ball, when it leaves, will leave at a right angle. So if the 9 ball goes in the corner, this cue ball is going to go in the side pocket. That's a foul, and that's how you lose the game. So this is pretty much an elastic collision. There's very little heat and sound, and you can see that they leave each other at 90 degrees. Okay, so what would we do with this question? Well, they told you that ball A went up at 30 degrees right here. So there has to be a 90-degree angle between A and B. That means that B goes down at 60. So you can just draw that in. You can go, oh, I know it's going to be 60. And then you can do it just like we've done before. Okay, our solutions that we've done before will be just fine. I would do a vector picture. I would say, hey, initially there's just the 4 times the 12, the 48. And then there are 2 momentums afterwards. And this is a really easy one because those 2 green momentums actually meet at a 90-degree angle. So when we drop in all the angles we know, then this one, you don't even need the sine law or the cosine law. You can just do SOHCAHTOA. Like for instance, you could do cosine of 30 is equal to momentum A finally on top of 48. You could find momentum A. And you could divide by 4 kilograms if you really want to know the speed. And you could do the exact same idea to try to find momentum B afterwards using perhaps sine of 30. And if you really wanted to know the speed, you could divide by that mass of 4. And that's pretty much the end, but let me just summarize with this. Okay, here's the expectations on you as a Physics 12 student for collisions. I would expect that you would use conservation of momentum to find one missing thing if it's a one-dimensional collision, just like we've done before spring break. Or if it's a two-dimensional collision, I would expect you to be ready to find two missing things. Generally, you would want to use the vector method, okay, with, maybe it's even just a right angle triangle with Pythagoras, or sine law and cosine law maybe. Or if you have to use the component method. Most people don't like using that unless they have to, okay, unless there are four momentums, or more than three, let's say that. Then, after you're done finding those missing things with momentum, then you could check the kinetic energies to see if the collision was elastic or not. Here's one extra little fact you can take to the bank. If, we saw this before the break, if it's elastic one-dimensional and they're equally massive, then they trade velocities. You can just say, I know that. That's what it's going to do. Or if it's elastic, two-dimensional, equally massive with one at rest, that's a lot of ifs, then they're going to scatter at 90 degrees. And that finishes all of our theory for collisions with Physics 12. We've got our one-dimensional and two-dimensional collisions that we'll use momentum to try to do some solutions for. It's your best friend. And then we'll check the kinetic energies out later to see if it was elastic or not.